Hi, I'm Martynas. This is a quick presentation of my dissertation project on injection attacks against automatic speech recognition systems. To start with, the motivation for this project was primarily the rapid growth in access to smart speakers. For example, just in the UK alone, smart speaker adoption rates more than doubled in 2018 in comparison to the year before. And with platforms like Hugging Face, pre-trained speech recognition models are becoming more accessible and are being used daily in a variety of projects by developers all around the world. And this dissertation project aims to highlight the risk of injection attacks against these modern ASR systems and models. So the attack scenario is the following. An adversary crafts a malicious voice command audio file, and this recording can be anyone's voice. It can be the adversary's voice, doesn't matter. The audio of this voice command is then distorted in such a way that a speech recognition system, for example, a mobile voice assistant like Google Assistant or Siri, understands what is being said, while a human perceives it as unintelligible noise. So the actual attack itself, it primarily relies on the fact that speech recognition systems are designed to only roughly capture the functionality of human hearing. It's not exactly the same thing. So this difference is this difference between human and machine hearing is what introduces vulnerabilities. And my attack particularly focused on exploiting ASR models, so speech recognition models that use the Mel frequency feature coefficients. These are the most common acoustic feature extraction, or this is the most common acoustic feature extraction algorithm among speech recognition models to this day. However, there are new ones coming out, such as end-to-end architectures. But back to the point. To exploit this extraction algorithm, these MEL coefficients can be extracted from an audio clip, and then using these coefficients, the audio can then be reconstructed. So since the reconstruction of audio from MFCC is lossy, distortion is then introduced, and then this level of distortion can be tweaked to achieve the desired results of the attack. As for results, I created an audio mangler script using MATLAB, and then also tested my generated audio samples using pre-trained ASR models with PyTorch. Then I conducted a small-scale in-person study where I asked participants to transcribe different audio samples. Participants were given 3 sets of audio, a set of noise-free, just English audiobook clips for a baseline evaluation of their ability to transcribe English language, and then 2 sets of malicious audio that ASR models could transcribe accurately. The percentages represent the average word error rate across these sample categories. As you can see, the second iteration of generated malicious samples were the hardest to correctly transcribe for participants on average. So to reiterate, sort of the aim of the project was to highlight the immediate threat of existing injection attacks against speech recognition systems. This attack is not necessarily new. It was proposed in a 2015 paper titled Cocaine Noodles by Vidya et al. Moreover, the concept of injection attacks has existed for decades, even before this paper, whether it be in web-based attacks, anything. So this project mainly highlights that these decade-old threats, they still apply to modern systems, even within speech recognition. Even a decade-old speech recognition attack, because of an unchanging speech recognition architecture, is still vulnerable to the same attack. Of course, the attack explored in this project does come with its own set of limitations. Firstly, the generation of malicious audio samples. It's a lengthy process requiring continuous trial and error, more specifically when operating under a black box level of knowledge. This is because all of the parameters required for MFCC extraction have to be manually and individually adjusted to achieve the desired result. However, if operating under a gray box level of knowledge, where an attacker trying to develop these samples, if they know the MFCC parameters used by the model they are attacking, it becomes an easier one variable minimization task. And then this is why the second iteration of generated audio performed better in the small scale human study. Another issue is that priming effects make it difficult to objectively test how perceptible an audio sample is to a human. For example, if a participant happens to know the transcript of the sample beforehand, they'll be able to understand what is being said very easily, no matter the distortion levels applied. The same applies to very simple patterns, like, for example, counting from 1 to 9. It's a very simple audio pattern that is easy to recognize, and is easy to recognize no matter the distortion levels as well. In terms of future work, the project can be extended in quite a few ways. For example, different types of distortion or perturbations can be applied to these generated samples to make it even less perceptible to humans, as proposed by Abdullah et al. And then also, of course, the attack can be tested against a wider suite of ASR models. And then also something not mentioned here, or not mentioned on the slide, is just looking into potential ways to try and automate the sample generation process, and minimize trial and error, especially for a black box level of knowledge. So lastly, if you'd like to learn more about the specifics of the project, here's a full poster. Hopefully it's visible in the video. But then you can also, of course, refer to my full dissertation paper. Thank you.